Alright guys, we're going to go ahead and get started with our lecture video on Lewis dot structures. Essentially in this lecture video we are going to apply the principles of covalent bonding that we have previously learned. We're going to use this knowledge in order to make covalent compounds or molecules. Now molecules are basically compounds that are made up of non-metal atoms that are covalently bonded to each other. And we can represent these molecules using a system or a method of Lewis dot structures. For example, in your notes here I have a molecule of ethane, C2H6, and the Lewis dot structure for this I will circle is right here. Notice that we use two dots between these two atoms, carbon and hydrogen, and those two dots are going to represent a covalent bond. Alright, and that is typical for any Lewis dot structural idea, is that we use two dots between atoms to represent a covalent bond. Okay, and we're going to show you how to put these structures together, and the rules apply here in just a minute. Now next to this is another structure of ethane. It's the same structure, except instead of using dots we replace those dots with dashed lines. And this is also another acceptable method to use. It's kind of an abbreviation of the Lewis dot structural methods. Today we're just going to focus on using dots though in our practices. Alright, so let's go ahead and take a look at some problems here using the following rules. Okay, so there are 6 rules that we need to apply when we make or draw a Lewis dot structure, and they're listed here in your notes, and so you need to become very comfortable with these steps or rules in drawing a Lewis dot structure. We are going to practice using these rules with real problems here, okay? But before we do that, I want to introduce a couple of terminology ideas or looks in a Lewis dot structure to understand these rules a little bit better as we apply. Okay, so let's take a look at here. We have 2 structures below that it's represented in your notes. The one on the left here is a Lewis dot structure of H2O or water. Alright, now notice that you have dots between the oxygen and hydrogen. Again, those represents the covalent bond between oxygen and hydrogen. So in this case, water forms 2 covalent bonds. The other dots here, and by the way, before we go on, when you only have 2 dots, that is considered a single bond or a single covalent bond. Alright, so water has 2 single covalent bonds. Now the other dots around water here, and I'm going to circle those, these ones here in black, those are known as lone pairs. Now what a lone pair is 2 dots that represents 2 valence electrons that are not bonded to any atom. Alright, so you simply just need to know what a lone pair is. Again, a lone pair is a representation of 2 dots or 2 valence electrons that are not bonded to any atom. Alright, now we also have double bonds that can be formed. Double bonds are represented by 4 dots. Alright, so such in this case of this molecule over here, that means basically we have 2 covalent bonds that are created between carbon and oxygen. Again, 2 covalent bonds. And so each covalent bond represents 2 electrons. Therefore, if we have 2 covalent bonds or a double bond, we're going to have 4 dots to represent it. Now we can also have a triple bond, all right? And so a triple bond just simply means that we have made 3 covalent bonds between the 2 atoms. So say we have atom X and atom Y. And to form a triple bond, we're going to have 6 dots between X and Y. And these 6 dots right there represent a triple bond that's formed between them. But in reality, a triple bond is just really 3 covalent bonds. So keep that in mind. Alright? So now let's go ahead and apply these to some practice problems here that are in your notes on the next page. What we're going to do is we're going to go ahead and use the rules that are in your notes to basically formulate the Lewis dot structure of these different compounds or molecules. Okay, so we're going to start off with hydrogen. All right. Now let's take a look at your rules. It says rule number 1 is you need to count the total number of valence electrons for each atom in a molecule. Well, hydrogen is made up of 2 atoms of hydrogen. So how many electrons does each one of those hydrogen have, or valence electrons? Well, hydrogen has 1 valence electron for each one, so that gives us a total of 2 valence electrons. So I'm going to go ahead and make note of that because that's really important. So now I've completed rule number 1, so I'll go to step 2. Step 2 says determine the central atom of the molecule. The central atom is usually the one that needs the most electrons to fill its outer shell. Well, we have 2 hydrogens here. Both of them need the same number of electrons, so they're both essentially going to be bonded to each other. Alright, so they're both going to be our central atom. So hydrogen. Alright, I'm going to just choose one of them. So now I got a central atom. Let's go to rule number 3. Rule number 3 says make a covalent bond between the central atom and the other atoms in the molecule by creating a bonding pair of electrons represented by 2 dots. Alright, so I'm going to do that. I'm going to create a bonding pair between my 2 hydrogens, and now I have completed rule number 3. Remember that the 2 dots in the bond represents the 2 valence electrons that are being shared between these 2 atoms. Alright, so I've done that. So let's go to rule number 4. Rule number 4 simply states this: subtract 2 electrons for each single covalent bond drawn in step 3 from the total number of valence electrons counted in the step 1. So what that means is I've used up 2 electrons here, so therefore I'm going to subtract 2 electrons from my total amount, and that gives me 0 electrons. Now, it is important, very important, that you use up all of the available valence electrons that you have. You have to use them all up. You cannot have any less or any more added to your structure. So in this case, I have completely used up all my valence electrons, so I can't do anything more. So I need to move basically to step 5. So step 5 says distribute the remaining electrons as lone pairs around the atoms. Well, I don't have any more electrons to distribute, so I cannot do step 5. However, I can do step 5b, and that is I can make sure that each of these atoms contains a full outer shell. Because remember, the whole purpose of chemical bonding is for these atoms to create a stable octet, or in the case of hydrogen or helium, they only need to have 2 valence electrons to have a complete full outer shell. In this case, each of the hydrogen is sharing 2 electrons, therefore each hydrogen has a complete full valence shell, and it is happy. So this is the Lewis dot structure of hydrogen. Alright, let's go to our next one, oxygen. Alright, step number 1 says that we need to count up the total number of valence electrons. So each oxygen has basically 6 valence electrons, so that gives us a total valence electron number of 12. Step 2 says determine the central atom, the one that needs the most electrons. Well, oxygen, there are 2 of them, so they both need the same number of electrons, so oxygen is our central atom. Step 3 says let's make a covalent bond between the rest of the atoms by using dots, and so the only other atom left is another oxygen. Okay. Step 4 says take the number of bonding electrons and subtract it from our original number. So that's what we're going to do. We have 2 bonding electrons, so 12 minus 2 is 10 remaining electrons. Okay. Now, step number 5 says that we distribute the remaining electrons around as lone pairs around the other atoms. Now, what's important is step 5A. Look closely at step 5A. It says start distributing these electrons from the outside atoms and then work your way inward. Well, in this case, we don't really have a solid central atom. They're both outward, so we're just going to start distributing electrons on each one of these. So 1, 2, 3, 4, 5, 6. So I've used up 6 out of the 10 remaining. 7, 8. Actually, I think I've done 2, 4, 6, 7, 8. 2, 4, 6, 8, 10. Yeah. So I've used them all up. So I have no more electrons to distribute around the oxygen. Okay, I've used up the remaining 10. So now what I have to do is go to step 5B and make sure that each atom has a complete octet. So that means I need to make sure that each of these oxygen atoms have 8 electrons around them. So let's take a look if that's the case. Let's look at the oxygen on the right. It has 2, 4, 6, 8 with the shared pair of electrons. So the oxygen on the right is completely fine. But what about the oxygen on the left? Again, we count, it has 2, 4, 6. Uh-oh, the oxygen on the right is deficient in 2 electrons. Well, what are we going to do? We have no more electrons to distribute around it. So we have a major issue here. Well, if you go to step 6, it will solve that problem for you. Step 6 says, if an atom is deficient of its octet, convert the lone pair from a neighboring atom into a bonding pair of electrons, thereby creating a double and or triple bonds. So what we're going to do is we're going to take, let's take this pair of electrons here on this oxygen, and we're going to go ahead and make a double bond between these 2 atoms. So a double bond, remember, is 4 electrons between them. Okay, now that should give us 2, 4, and each one of these, so 6, each one of the double bonds, so 6, 8. So each oxygen now has the appropriate number of valence electrons, 8 electrons, creating that double bond. So let's clean this up a little bit for you and show you the final structure, Lewis structure for oxygen should look like this. We have a double bond between them. and we have 2 lone pairs on each one, like so. Alright, and that gives us an example of oxygen. Alright, now let's go to our next one here that we have listed, which is HCl. Alright, so step 1 again says count up the total number of valence electrons. So if we do that, chlorine has 7 and hydrogen has 1, so the valence electron number should be 8. Alright, now let's look at step 2. It says find a central atom. The central atom is the one that needs the most electrons. Alright, so in this case, really the one that certainly needs the most would be more or less, well, I mean, it's pretty even kill, really. Hydrogen needs 1 more to have 2 to have a complete outer shell, and chlorine only needs 1 more to have a complete outer shell. So essentially, they're both central atoms. So let's go ahead and just prick 1, and we'll say hydrogen is our central atom, since it's written first. Alright, and then step 3 says let's go ahead and use dots to make our covalent bond between the chlorine, like so. And then we got to take those 2 electrons and subtract it from our 8, and that will give us essentially 6 left. And then we're going to distribute the remaining 6 electrons around the atom. So let's start with chlorine. So chlorine has 1, 2, 3, 4, 5, 6. So we've used up all 6 of them on chlorine. So now let's see if every atom has a complete full outer shell. Well, the chlorine, if you count them up, the chlorine has 2, 4, 6, 8 electrons, so chlorine is good. And the hydrogen is also good because it only needs 2 electrons to make itself have a complete shell, and so it does that with that single bond. Alright, so there is HCl for us. All done. Alright. Alright, let's go on here. I know we're getting on to 20 minutes, and I don't want to go much longer on this. So what we're going to do is I'm going to choose a couple more to go through, and then in class we'll finish these up. Alright, so let us choose H2S. Alright, so H2S, sulfur has basically 6 valence electrons, and hydrogen, each of those has 2. So the valence electron number should essentially be equal 8. Okay? Now, which one should be our central atom? That's step 2. Well, which one needs the most? Well, sulfur needs the most valence electrons. So we're going to go ahead and put sulfur as our central atom. Alright, and then the next step, step 3, is we need to make a bond between the sulfur and the hydrogen. So I'm going to do that. Make a bond between those. Another bond, like so. Alright. Now, the next step is to take our valence electrons that we used to create bonds and subtract it. So that would be 4. And so we have 4 remaining. Okay? 4 remaining electrons. Now, what do we do with these 4 remaining electrons? Well, we distribute them around the remaining atoms. And we always start out with the outside atoms first, and then work our way to the central atom. Well, the outside atoms are hydrogens. So the question is, does hydrogen need any more electrons? The answer is no, they don't need any more electrons. So essentially what we're going to do is go to our central atom, which is sulfur, and we're going to finish up creating, distributing those last remaining electrons around sulfur. 1, 2, 3, 4. And that uses up the remaining 4 electrons that we need to complete a full octet for sulfur. And sulfur becomes a happy atom. Alright? So this is the final Lewis dot structure for H2S, where we have created 2 lone pairs of electrons on the sulfur, and we have 2 covalent bonds, one between the sulfur and each of the hydrogens. Alright, so that's essentially it. Alright, so I've gone beyond the time frame on this lecture video that I want to do. What you might want to do is go through the remaining of these problems on your own and see if you can figure out what their Lewis dot structures are, and then we can check them in class. Alright, so I'm going to sign off on the video from here.